All right, let's talk about Lab 3. If you're working on it, you know the deal. You've got a bunch of raw sensor data, and you have to make sense of it. Well, in this guide, we're going to walk through the professional AI workflow step by step to show you exactly how to build a really powerful predictive model. Let's dive in.
So this is the big question, right? It's what every engineer faces when they get a new sensor. You have this stream of numbers, a file packed with readings, but what's the story it's trying to tell you? How do you actually turn that raw information into a tool that can predict what's going to happen next? That's exactly what we're here to solve.
And here's our game plan. First, we'll break down the problem itself. Then, we'll get into our main tool for the job, machine learning. After that, we'll walk through the exact workflow a professional would use to build and test a model. And finally, we'll connect the dots and see how this lab project sets you up for your career.
Okay, first things first, let's get super clear on the task at hand. I want you to think of your data set less like a file and more like a puzzle. It's holding a secret, a hidden relationship between physical forces, and our job is to crack that secret wide open.
So for this lab specifically, here's the setup. You've got two inputs. These are the resistance readings coming from two different electrodes, and your target, the thing you want to predict, is the physical strain being measured. So the mission, if you choose to accept it, is to build a model that can take those two resistance numbers and accurately predict the strain. Simple as that.
So how in the world do we find that hidden relationship between resistance and strain? I mean, we could try to sit down and write out a bunch of crazy complex physics equations by hand, or we could use a way more powerful, modern approach. Let's talk about the solution here, machine learning.
Now, the most important part of that definition is the phrase without being explicitly programmed. Think about that for a second. Instead of us needing to figure out all the perfect math and write the exact formula, we just show the computer the data. We give it the inputs, and we show it the correct outputs over and over, and we let it figure out the relationship. That right there is the magic of this whole thing.
And just to show you where this fits in the grand scheme of things, machine learning isn't some totally separate thing. It's a core piece of artificial intelligence. You can see from this diagram, it's pretty much the engine that lets AI systems learn from data. And deep learning, which is what we'll be using, is a really powerful technique inside of machine learning that's inspired by how our own brains work.
So, how does a real AI engineer actually build one of these models? It's not just random guessing, I can tell you that. There is a very systematic, proven process that takes you all the way from that raw data to a final working predictive model. This is the industry-standard workflow.
And here are the steps. You start by getting and cleaning up your data, which luckily for you has already been done in this lab. Then you pick a model, you train it, and then, and this is so important, you evaluate how well it's performing. Based on that evaluation, you go back and tune it to make it even better before you finally put it out into the world to do its job.
This flowchart just lays it all out perfectly. You can really see that cycle happening. We train the model, we evaluate it, and then we fine-tune it. That little loop right there, the evaluation and tuning, that's where you take your model from just a good guess and turn it into a precision instrument. This whole diagram is your guide, not just for this lab, but for projects you'll do in the real world.
All right, enough theory. Let's get practical. Following our workflow, we're now at steps 3 and 4, choosing a model and training it. This is where we go from the abstract idea of a model and actually turn it into a real piece of software.
So on the left, you've got this sort of black box idea, right? Inputs go in and output comes out. But what's actually inside the box? Well, for this lab, we're going to use the architecture you see on the right, a neural network. You can see our two inputs, the resistance values, feeding into some hidden layers and then producing our one single output, the strain.
So what are those layers made of? They're made of these things called artificial neurons. Think of each neuron as a tiny calculator. It takes in some information, multiplies it by an internal value called a weight, and then applies a mathematical function to it. By tweaking thousands of these tiny weights over and over again, the network as a whole slowly but surely learns to map the inputs to the outputs.
Okay, so we've built a couple of different models. Are we done? No way, absolutely not. Now comes what I think is the most critical step for any engineer, evaluation. How do we know which model is actually the best one? We can't just guess. We need cold, hard numbers. We need metrics.
So let's look at some real results. Here we're comparing two different models. Model 2 has one layer and Model 3 has two. Now to judge them, we're using two key numbers. The first is mean absolute error, or MAE. That's basically the average amount our prediction was wrong by. So for that one, lower is better. The second is R squared.
That tells us how much of the data's behavior our model can actually explain. For that one, we want to be as close to 1 as possible. So, looking at the table, which model is the clear winner here?
And the report confirms it. This is a really crucial point, you guys. Just making a layer bigger, stuffing more neurons into it, doesn't automatically make your model better. In this specific case, creating a deeper, more complex structure with 2 layers gave us a lower error and a higher R-squared. Model 3 is our champion, for sure.
And let's just focus on that winning R-squared score for a second. 0.91. That is a fantastic result. You know what that means? It means our model, just by looking at those 2 resistance inputs, can successfully explain 91% of what's happening with the strain. We didn't just build a model, we built a seriously powerful and accurate predictive tool.
Okay, so let's zoom all the way out. We've gone deep into the details of Lab 3, but why does this whole process, this workflow, actually matter for your future?
Because what you just learned how to do, this isn't just a lab. It's the fundamental, repeatable workflow for solving almost any problem that involves sensor data and AI. It doesn't matter if you're working with temperature, pressure, vibration, sound, or even images from a camera. This process of preparing data, selecting a model, training it, and then rigorously evaluating it, that is the key to turning data into real insight and real value.
So as you're finishing up your report, try to think beyond just this one assignment. You now have the blueprint for building intelligent systems. This workflow is a tool, a really powerful one, that can unlock the secrets hidden inside data. The only question left is, what are you going to build with it?